I think it is there. Yeah.
Yeah, so I've already shared a screen. So let's just see if it's working. Okay.
Hello, everyone.
Okay.
Yeah.
So shall we wait? Okay, let's wait for a couple of more
Let's
minutes
wait for 5
because
minutes. Yeah, yeah, yeah.
yeah,
Sure.
yeah, sure.
Am I audible? Am I clear? So people who are watching me on YouTube, they can at least comment on the YouTube chat itself. Even that would help. Yeah. Thank you. So we'll begin at 5 or so.
Yes, yes, we'll start at 5 sharp.
Yeah.
So Chinmay, I think we can start now. It's
Okay.
almost 5. So
Sure.
a very good afternoon to everyone present here. My name is Saurabh. I'm from Stellar Universe. So today we are going to have a talk by Chinmay. So today we are going to have talk by Chinmay. He's doing his MSc Physics Honors plus BE Honors Mechanical Engineering from Pilani, uh, Goa campus. So today he'll be talking on post-Newtonian theory and gravitational waves. And so over to you, Chinmay.
Thank you, Saurabh. Thank you. So yes, this is me, Chinmay, and I will be talking about post-Newton theory and gravitational waves. I am from Pilani, Goa, as Saurabh introduced, and so this talk is pretty much an introduction to the field. I don't think I can go very deep into it because that will take much longer, and we can't cover that much in this 1 hour or less, or even around in 1 hour. So yeah, so the overview of the talk will be something like that. We'll first discuss some good references, then we'll see why post-Newtonian theory is at all required, and what actually is this post-Newtonian theory, and some mathematics involved in it. Next, we'll move on to understanding how gravitational wave works, and then we'll share some plots that we got while doing our study. So I really think that these books, the first book by Poisson and Will, which is called Gravity, it is a really good reference book to start with. In fact, uh, it's not just for post-Newtonian approximations, but you can also use it to study a whole of general relativity. It's a really good book. Then we have a very specialized booklet by Eric Poisson, and then there is this very famous book by Charles Misner, which is called Gravity, Gravitation, booklet on gravitational waves from inspiraling compact binaries is very informative. And so, as to study this topic, we need a little bit of background in general relativity, a little bit of differential geometry, linear algebra, and some knowledge of differential equations. Yeah, so why do we need post-Newtonian theory? So we know that understanding any physical phenomena, any, be it apple falling down, be it cycle going ahead, any physical phenomenon is incomplete. I mean, if we cannot understand it completely, we can do is go more close to the actual phenomenon that is happening. We can just try to explain it better than we were able to previously. So Newtonian gravity, which is the the breakthrough in the field of physics, well, that is a great theory, and it explains gravity to a great extent. uh, we know that if there are two bodies, then the force between them, or the field between them, is inversely proportional to the distance between them and is directly proportional to the product of the masses. That was Newton's gravity. Einstein explained it a little further in a different way. He said that gravity or mass is nothing but something that causes a dent in in a fabric of space time. Well, this fabric of space time is something geometrical, right? And the mass is something physical. He was very beautifully able to relate these two, and he gave this beautiful equation, if you can see my cursor, which is known as the Einstein's field equations. The left hand side shows how the space time, or the how the geometry of space time is, and the right hand shows the mass or the material properties of the bodies. So Einstein's field equation, if you see these terms on the left hand side, these are highly non-linear in nature. And for this reason, it is very difficult to solve this equation analytically. In fact, it is almost impossible to solve it analytically. All we have to do to solve this is go numerical, or we have to use some approximations. So one of the method to solve this Einstein field equation is called the post-Newtonian approximation. And this post-Newtonian approximation is used to solve this equation in the domain of weak field zone. Weak field, as in if we are very far away from a body, or from a heavy body, that would be a weak field zone. Or weak field zones would be if there is an event happening and we are away from it to, I mean, if we are not in direct vicinity of the heavy mass, then we are in the weak field zone. And post-Newtonian approximation is used to solve this equation in this zone. So, okay, now we start with a little bit of mathematics of post-Newtonian approximations. So, what we want to do is solve this Einstein's field equation in weak field zone. So, for that, we have to introduce a formalism. And we'll go very mechanically over here. We want to convert the Einstein's field equation into a different form, which is called as relaxed Einstein field equation. And for that, we use something like this. The metric that we know over here, this metric is written as a Gothic metric, which is nothing but something denoted in this fashion, and that is used to define a new term which is called H alpha mu nu, H alpha beta mu, H alpha mu beta nu. And it is observed that of this term double derivative of this term gives us something of this sort. And we observe that the stress energy tensor that was seen in the Einstein's field equation over here is also present in the left right hand side of this, also present in this term. So we now we move ahead and we introduce a harmonic gauge on this on the potential, or the deviation from the this potential is nothing but deviation from the background metric. And we say that we impose an harmonic gauge, which is something of this sort. These couple of equations lead us to something lead us to an expression of this form, mm, which in turn is used to define a new wave like equation, which is given over here. Now the left hand side that we see is nothing but de-alembertion on the potential or deviation from the background metric, and the right hand side is nothing but the stress energy pseudo tensor. Why is it stress energy pseudo tensor? Because it has this stress energy momentum tensor and a couple of extra terms which are which are something that we'll need more time to explain, so we'll just skip through it right now. Yeah, so Einstein's field equation has been now converted into a relaxed Einstein field equation and some gauge, which this is conservation of stress energy momentum pseudo tensor, which is very analogous to this harmonic gauge on the potential. Yeah, so if we look over here, this is very similar to a wave equation. Which is for example, wave equation. For an example of wave equation, we can look at a Poisson's equation and any kind of wave equation. So we see that there is some we need a Green's function to solve this wave equation. Now, while we want to solve this wave equation, we want to look at the past light cone, because anything that has happened or any event that has happened is going to be in the past part of the light cone. Let's say that the event happened right over here where my cursor is, or is my cursor visible to all? It'll be nice if someone can tell me.
No, your cursor isn't visible.
Okay, my cursor is not visible. Okay.
Maybe
So you see
it
this
is,
blue.
but it's
Oh, okay. So here's my cursor. Here's my cursor. Try to follow it. And right here, somewhere in the middle of the blue spot, is our source. Now, let's say that the source gives out some information and the information travels like a wave. So let's say that the distance of one wavelength of that wave would would circle a region which is called the near zone, which is very close to the source, and all rest of the past light cone is called the wave zone or the far zone. This is the near zone and this is the far zone. This distinction is needed for mathematical purposes, otherwise we don't need it for physics. But we'll see later that how these two zones affect the calculations. Yeah. So we know that there is this relaxed Einstein field equation, and now we want to solve it in some way. And the method we use over here is called Post-Newtonian approximation. And this approximation method is explained somewhat like this. The potential term, can be expanded, I mean Taylor expanded kind of, into multiple terms which drop in order, which have higher order terms whose value or whose magnitude drops by g squared. Yeah. So now our job is to find out this H alpha beta and solve this relaxed Einstein field equation. So the method is very simple. First of all, we choose. Okay, let me explain. Let me clarify this. The metric, the metric of the space time of the observer is nothing but local metric, local or the background metric plus this disturbance. Yeah. So now first at zeroth order, what we'll do, we'll take this as zero. Then we'll evaluate the stress energy momentum pseudo tensor, which is a function of h alpha beta. And that stress energy pseudo tensor we'll substitute over here and obtain a new h alpha beta. Now this h alpha beta can be written as the first order solution or the first order value of the h alpha beta. Then we put it again in this expression for the stress energy pseudo tensor, and that in turn goes over here and we find a new term of h alpha beta, which goes again up in the equation. So we see that this is an iterative process. With each and every successive iteration, all we do is just take a new term, we include one new term to h alpha beta, and we keep deriving. Now this process looks easy, but it gets a little tricky later on. We'll see that later. So after the second order iteration itself, I was too tired, and I mean, a lot of math goes into it, and these results are obtained. I mean, you'll see that this is the near zone expression for h alpha beta. H alpha beta is alpha beta can take values from 0, 1, 2, 3, right? And 0 is the time coordinate, 1, 2, 3 are the space coordinates. So h00, which will be the time part of the time part of the potential, it takes some value, or it takes the value something like this, while the others look something like this. And we see that there are few terms over here, u, x, psi, p. These are nothing but some scalar potentials, and which have their counterparts of vector and tensor potentials in this form. Now, if you see, this first term is the only Newtonian part. The rest terms fall with the the next iteration or the next order of the value is 1 by c square times less as compared to this one, which means that this is significantly the value of this is significantly less than the Newtonian part. Hence we can safely say that Newton was correct to a great extent. In fact, the correction that came in later was 1 upon c square times the value of the values that were previously present. Yeah. And yeah, so 1 upon c square is the Newtonian part, and similar is the case over here. Here you will see that this is nothing but 4 gm upon r is nothing but the Newtonian potential itself. These are the wave potential terms and wave zone potential terms, and this is the near zone potential terms. Cool. So I think we'll take a little bit of break over here. Does anyone have any questions? Am I audible?
Yeah, you're audible.
Yeah, so let me know if there are any questions. Okay, the near zone. Yeah. So the near zone is nothing but a region. It's a region where we assume that there is strong gravity from the source, and it is okay. The radius of, let's assume that the source is a point, right? And it is emitting some gravitational wave. Let's call it a gravitational wave for right now. So 1 lambda of this gravitational wave, we take that as a radius, and make a circle centered at this source, and the region that we'll get over there will be the near zone. Is that helpful? Okay. Karnika Bharadwaj, is that helpful? Okay, cool. And the next question is, what does the region outside the light cone represent? It is okay. It is called. I don't know what we are supposed to call it, but it is an inaccessible zone. I mean, imagine this. That okay, light cone. I think I'll have to explain light cone for that. So light cone is a, a coordinate system, or it's a graph which has the z axis. The axis going through this cone is the time axis, and the axis and the plane perpendicular to the screen is the space coordinate, or the xy coordinate. In fact, it is supposed to be all three spatial coordinates, but we represented like this. Now, if you were to move at speed of light, yeah, if you were to move at speed of light, then you would be following this particular edge of the cone, or any of the edges of the cone. And if you were to be faster than speed of light, then you were to be outside the cone. We don't want that. I mean, that's not possible according to special relativity, and for that reason, it is we cannot access anything that is outside the cone. Yeah, maybe it's called the casually disconnected region. Yeah, space like region, actually. Okay. Okay. Next question is, what is the use of REFE over EFE? Well, EFE, solving the EFE. If you see over here, EFE is highly non-linear. I mean, this RIK and the R over here, the Ricci tensor and Ricci scalar Riemannian tensors, these are very difficult to evaluate, and we cannot actually basically evaluate them using analytically. And when we introduced this Landau-Lifshitz formulation, what we did is that we changed the metric so as to look something like this, right? And now the h and the deviation from the background metric, this capital H, the deviation from the background metric is written as small h alpha beta. Now this h alpha beta is easily is easily solvable, or it can be evaluated easily by using some approximation, by basically Taylor expanding it, and that cannot happen over here. For that reason, we use the relaxed Einstein field equations instead of normal Einstein field equation. Yeah, so we'll move ahead now. Yeah, so to the exciting part. Uh, I think there's some lag in my screen. Yeah, so are we all seeing the gravitational wave? I mean, the cartoon of the two balls going around each other and generating some waves? Okay, I'm able to see it anyways. So, yeah, moving on. So, okay. So the universe has a network of some four-dimensional space-time fabric. Let's assume it's something like that. Now, Einstein says that mass affects curvature, right? And that curvature in turn affects the motion of the mass, because if there is curvature, the mass is bound to roll into it, or mass is bound to move a little bit inside it. So it explains the Einstein field equation kind of explains how mass affects the curvature and how curvature will in turn affect the mass. Now, look at this heavy sphere in this fabric. which has caused this big curvature. Now, this sphere, if was supposed to break or if was supposed to go through some kind of event, right? It is going to create some disturbance in the local fabric, right? And that disturbance is postulated to move with the speed of light, so as to reach the observer who is sitting somewhere on some other position. Yeah. And it is also postulated that if there is a disturbance in some medium, this disturbance has to travel in form of gravitational waves, in form of waves. And since we are talking about space-time, hence gravitational waves. And one good thing about gravitational waves is that the propagation of these gravitational waves is unaffected. It is unaffected by any other body which it has to pass through. Yeah. So the gravitational wave, it looks something like this. I don't think it is. I don't think you are able to see the screen yet. Yeah. Yeah. So gravitational field moves. The gravitational field causes a strain in the local space time from wherever it travels. Yeah. And that strain looks something like this. First, this is the time axis, and this the vertical axis is the strain. So the strain is sinusoidal for a while, and then and then the amplitude of the strain increases while the frequency decreases, and later it dies out. This particular this particular wave that we see over here is a template of two spinning bodies, two very compact bodies spinning around each other. They are in inspiral mode from this to this region. The zone which says inspiral, that is where they are just moving around each other because of their mutual gravity. Where you see merger is when they actually come in, when they're very close to each other and are all they've started coalescing. And the ring down is when the two bodies become one and just wiggle, so as before they settle completely. So post-Newtonian theory is able to, the post-Newtonian approximations that we used previously, that we saw previously, they can be used to explain the strain till this point, right before the merger point, which is the longest part of the gravitational wave. Post-Newtonian approximations are helpful in obtaining that, and we'll see that in the upcoming slides. Yeah. So before that, I think we'll need some background um, on the mathematics that is going to be used further. Yeah. So we see this blue dot. We'll call it the Earth, and you see that Earth has caused some distortion in, or not distortion, but the some curvature in the local space time, but that is negligible. Hence, we can assume, that curvature of this blue ball compared to the curvature of these heavy masses, the blue ball is literally in a flat space time, we can assume, right? So we will assume that there is flat space-time at the observer, in the region where observer is present, and that's over here. And that would mean that the Riemann tensor is zero. Riemann tensor is a Riemann tensor is something that defines, or something that explains curvature. If there is non-zero Riemann tensor, then we have we do have curvature. And if there is zero Riemann tensor, then that's a flat space-time, or flat region. Yeah. So now the source of disturbances, let the source be either the blue or the red ball. If there are disturbances, these disturbances will travel and reach the observer on the blue ball. Blue is the Earth, so it will reach Earth, and the disturbance will travel through the fabric of space-time, which means that there will be disturbances in the metric of the space-time. And these disturbances can be of multiple orders, okay, I have a plot that I can show to explain what this high order disturbances mean. Yeah. So I actually changed the screen, but no one can see it yet. Yeah. Yeah. So we see that this is almost a circle, right? This is almost a circle. Now, if I were to zoom into this, I see that there are some disturbances. Yeah. Now, these disturbances can be called as first order disturbances. I mean, there is disturbance in the in the normal sphere, in the normal circle. Now, if I were to zoom a little more, I'll see that there are higher level disturbances in the previously known disturbance, right? Which are much smaller than the previous disturbance. So this is the second order of disturbance, which second order of disturbance, and we don't have to go till here. We are happy to stay outside this and just look at the first order of disturbance and do the calculations further, because they are sufficient enough to give us information about the gravitational waves. Yeah. So you see the local metric is nothing but summation of the background metric, which was a flat space-time, plus some disturbances. Yeah. Now, what we will do next is we'll ignore these these higher order disturbances, and we'll just play and figure out how the first order of disturbance looks like. Yeah. So curvature of the space-time is also similarly explained. I mean, the curvature of the local space-time will then become the curvature of the background, which is without the disturbance, plus the curvature because of the disturbance. Now, since there is no curvature to the background, because we are in a Minkowskian space-time or the flat space-time, hence there is no curvature. So all curvature that we have is because of the gravitational wave or the disturbances. Yeah. Yeah. So now that we know that disturbances travel as waves, let's solve these. Let's mathematically understand these disturbances as waves. So let's assume, since the source of these waves is infinitely far away from the observer, we can safely assume that the disturbances or the waves, when they reach us, have plane wave solutions, or they are like they travel as plane waves now, right? And the plane wave solution is given something like this. I don't feel the need to explain this equation, but still, the wave, that is the plane wave that we are receiving at the observer end, has some amplitude a mu nu and has a propagation vector ka, while xa is nothing but the position of the or the distance of the wave from the source. Yeah. So this particular wave solution has a number of restrictions. These restrictions are obtained by some properties of waves, which mean one of them is k lower index a and k upper index a. Product of k lower index and k upper index is 0. The next property of the wave is I mean, you can just read it. Mu alpha and a mu a and k up index a is 0. The next constraint is that the wave is transverse in nature, which means that the propagation is perpendicular to the amplitude or to the oscillations. The propagation of the wave is perpendicular to the oscillations in the wave. Yeah. And next property of this wave is that it is trace free. This trace free is something that involves a little bit of math, so we'll skip through it right now. And these sum up to total number of 8 constraints. And these constitute of 8 constraints. Now, out of 10 independent terms, there are 8 constraints, which leaves us with 2 degree of freedom to the wave. Now, these two degree of freedom are are given as or can be seen as two polarizations of the waves. Yeah, these polarizations are something like this. They are, I mean, the elongation and the compression of the wave can be along the axis or can be totally off the axis. These are the two polarization. The first one being the plus polarization, and the next one being cross polarization. Yeah. So binary systems. So the gravitational waves that the whole world is actually interested in right now are originated from binary systems. So what are binary systems? They are nothing but two compact bodies. I mean, they can be any bodies, but waves that we observe come from two compact objects, which go around each other and finally collapse into each other and merge, right? So let's say that the two compact objects have masses m1 and m2, and and the sum of the masses is m1 plus m2. Reduced mass is a parameter which is given as product of the masses which is given as the ratio of product of the masses to square of the sum of the masses. And the observer, which is very far away from the binary, chooses two directions, e phi and e theta. These two directions are used to observe the polarization of the waves. Yeah, cool. So the previously the we remember the potentials that we had discussed previously, which were given in the near and far zone, right? These potentials. So these spatial terms, the one over here and the one over here, are the ones which we are going to actually use, because we observe these gravitational waves as changes in the length of a system. And when we want to measure the changes in the length of a system, we want only spatial terms of the potential. Hence we are only concerned about this HAB and HAB of near zone and HAB of the far zone. Now these HAB and HAB of near zone and far zone, they need to be converted into the transverse and trace free gauge, so that we can observe we have a potential, but that potential or that field is just a disturbance. Now we want to observe that disturbance as a wave, and for that reason we converted it into we convert the disturbance into this transverse trace free gauge, as discussed previously in the as the solution for the plane wave solution. Sorry. Yeah. So we convert it into that, and we observe that that can be written as H cross or plus polarization can be written as uh, zeroth order term and plus higher order post-Newtonian terms. You see the tail over here? This tail is nothing but this tail term is nothing but a term which involves which explains the whole history of the event, starting from zero, time is equal to zero. I mean, this mathematically, this term a plus tail or a cross tail only means that it mathematically is an integration from zero till infinity, which means that we are going infinitely back in time to evaluate this term. So it contains all the history of the system, while these terms are just higher order terms for H plus or H cross. Yeah. So as we saw that H plus and H cross can be written as summation over zeroth order and higher order terms. These higher order terms, I don't think we can discuss it here right now, because you see that in the first order term is nothing, it's simple. Second order term, I mean 1.5 order term is still fine, but even higher order terms, like look at this 5 by 2 order term, it takes almost the whole page to even understand it. So yeah, so but with each higher order term we discover a new phenomena, or a new property of the system. For example, at zeroth order, we have nothing but Newton's gravity. At first order, what we see is the precession of the orbit in which, I mean, the elliptical orbit of, say, any celestial object. We see that it can have precision, and this precision can be explained by the first order approximation to these fields. The higher order approximation gives subsequent explain the subsequent physics in the of the for the system. In fact, at 1.5 order PN, 1.5 post-Newtonian order, we don't have a decay of orbitals. So if there are two bodies going around each other, they are eternally and infinitely going to go around each other no matter what. But if we just go to if we go one order ahead, which is to 2.2.5 order, we'll see that there is a term which explains, which explains, or which tells us that the orbit is going to shrink, or the bodies are going to come closer because they are emitting gravitational waves. So the first plot that we see over here is of the gravitational wave from a system which does not the radius of these two bodies, when does not drop, not radius, actually distance between these two bodies, if it does not drop, then we have this particular wave. While if we introduce third PN solution, the wave clearly starts to the amplitude of wave clearly starts to increase, and which tells us that the bodies are coming closer to each other and they're getting more and more violent. We can't go beyond this because they're so close now. Beyond this point where the second gravitational second plot ends, at this point we say that they are going to merge now, or I mean they're effectively touching each other, so they are going to merge now. And for that reason, PN post-Newtonian approximation, which is an approximation or a theory limited to weak field, we cannot use it over there. So hence the gravitational wave can only be plotted till this extent. Yeah, so here I would like to conclude. I'd be happy to take any questions. Do we have any questions? Oh, so the question would be on YouTube, right? Yeah. So Mehak Arora, okay. I'm not sure if I understand this question. Do there is any time dependent constraint? I don't understand this question completely, but let me try answering it. So you're asking if these bodies going around each other, which give out gravitational waves, are the properties of this gravitational wave dependent on time? Yes, they are dependent on time, but the thing is, their dependence on time can be seen in the first plot of the gravitational wave itself, which says that the strain due to gravitational wave increases and decreases as the time passes. Now this extent, or the amplitude of this strain, increases even further, but that information is not there in the first 1.5 order PN solution. That information is only obtained from 2.5 order onwards. So you see over here in this equation, all the first plot that we have here, we use this same equation, but only for p is equal to 0 to p is equal to 4 or maybe 3. But for p is equal to 0 to p is equal to uh, anything above 5 would give us the second plot. The second plot shows how time affects the amplitude of gravitational wave, or amplitude as well as the frequency of gravitational wave. Have I answered your question?
Maybe we can move on to next question, Chinmay.
Okay, okay, we'll move on to the next question. Is there any for okay, yeah, okay, for the okay, for solving strong field zone, yes, so we can't use post-Newtonian theory for that, and post-Newtonian theory is the place where I have limited myself as of now. But yes, we have more methods like numerical relativity. We have effective one body problem. These are significantly different methods to solve the Einstein field equation and to obtain the precise part of the gravitational wave beyond the inspiral, which can be seen in this plot. I'm not sure if you can see it right now yet. Yeah, so beyond the inspiral, merger and ring down, they can be modeled using effective one body problem and as well as numerical relativity. And there is gravitational, okay, gravitational wave is not dependent on anything. Gravitational wave is like plucking a string that has been tightly tied to two ends. So gravitational wave is going to happen if there is any event. It's just that how capable are we to observe it. For example, if there are two bodies playing around each other, to any size of bodies playing around each other, we'll be able to obtain gravitational waves. But only if the bodies are heavy enough, and only if the bodies are massive enough, we'll be able to observe these gravitational fields. If you see over here, the strain is of the order 10 power minus 20. This is still just the simulation for two black holes which are at around 20 times mass of sun. If there are two black holes which are 20 times mass of sun, and if they are at a distance of the distance is basically from here to Andromeda galaxy, and if the two bodies are over there, then we'll see a gravitational wave which is of the order 10 power minus 20, which means if we have an observer, if we have a apparatus of the length 1 meter, the strain or the difference in this length is going to be 1 upon 10 power 20 meters. I mean, it is that small. So it is very difficult to observe the gravitational wave. But yeah, it is every event in the universe will cause gravitational wave, because it is nothing but some disturbance traveling through space-time. So I'll move to the next question. I hope it was answered. If I haven't answered, or if I've been not very clear about something, please do let me know. And you can also drop me an email. I mean, if it is a really long question or something, I can answer it to you on the email. Yeah. So the next question is it observed that our moon is going centimeter away every year? Is this because of gravitational waves or else? Oh well, good question. So yeah, uh, moon might be going from us in a because okay, moon might be going away from us, or moon might be coming closer to us. Whatever it is, there has to be an explanation, and that explanation can be that explanation is more physical if we are able to observe the gravitational waves from this thing. But the problem is, moon and us, we are in the same system, and observing the gravitational wave in the same system is going to be very difficult, because we are too close to it, and plus moon is very light an object, so is earth. So yeah, the moon might be going away or moon might be coming towards us. It is going to give out gravitational waves, but explaining that using gravitational waves is difficult, because observing that gravitational wave is difficult. Like PN only works till weak field. Yes, PN only works till weak field. I know there are so many negative words in this: weak field, limited, but we did not have any other choice for a really long time, almost say 50 years or something. Can Riemann tensor be negative? Okay, that is a question that will require more time to explain, and I mean, I'll have to think over it. Uh, I'll be glad if you drop me a mail. I mean, I'll be glad to discuss that as well. I didn't get how lambda obtained from h gives another h. Oh, you skipped that. Oh, so sorry. So this is me answering Bhuvan SV. Yeah. Okay. So the lambda we have over here, it has the okay. We know stress energy momentum normal tensor, right? It has the properties of every body, every moving body. Now, you see this T subscript LL, superscript alpha beta, that is called the Landau-Lifshitz pseudotensor. That comes because of this formulation. This formulation of which is called the Landau-Lifshitz formulation. This term only appears over here. I mean, if you just subtract this term, I mean, double derivative of this term with respect and subtract it by the stress energy tensor into these factors, remainder of that part is called Landau-Lifshitz pseudo tensor. It's just some mathematical construct. Yeah. Now, if we impose this condition, which is called the harmonic gauge condition, over here in the previous equation, we see that we obtain something like this, and this term in turn becomes the th. Th is the harmonic gauge pseudo tensor. Yeah. So this th is nothing but something over here. So adding these two terms to the stress energy to stress energy tensor gives us a new quantity, which is called and this is nothing but a new form of the Einstein field equation. Yeah, so we are clear about what lambda is actually. Lambda is nothing but stress energy tensor plus a couple of terms introduced because of a little more introduction, a little more involvement of math. Now, what we do over here in the solution for relaxed Einstein field equation, first of all, we take the metric, the spacetime metric, to be the local metric only without any disturbance. Yeah. So using that metric, we have that metric now, and this Landau-Lifshitz the stress energy pseudo tensor, that is lambda alpha beta. Lambda alpha beta is actually nothing but the stress energy tensor, which is given in terms of the metric, the Landau-Lifshitz tensor pseudo tensor, which is given in terms of metric, and the harmonic pseudo tensor, harmonic gauge pseudo tensor, which is also given in terms of the metric. Now, since we have the zeroth order of the zeroth order of h, okay, we have that zeroth order of h, which means zeroth order of h is nothing but zero. So that gives us the the local space-time metric, which is nothing but background metric plus the correction metric, that is the h metric, h term. And since that is zero, we get the Minkowski metric, right? Now this Minkowski metric we use to find the lambda zero term. Now this lambda zero term goes into the relaxed Einstein field equation. Solving this relaxed Einstein field equation gives us a new h. Now what we say that this new h is nothing but the first order correction to the previous h, and the previous h was zero. So it is just going to be this. It's just going to be gk1 alpha beta, and that gives us a new metric. Now this new metric again put it into the expression for lambda. It gives us lambda to the first order, right? Now we keep doing that, and we keep on increasing the terms in the expression for h, and we keep getting higher order terms. Does that help, Bhuvan SV? Okay, please don't call me sir, for just for further reference. Please don't call me sir. Okay, Bhuvan got it. Cool. So next is MO or MOMO. Um, can you explain the physical meaning of one first order, second order disturbance in the gravitational waves again? Yes. So yeah. Okay. So imagine I'll go back to this figure. Imagine there is a tight string. Hmm. Imagine this is a very tight string, very tight body, or imagine this as a rubber ball, two-dimensional rubber ball or a ring, right? And you hit it with over here somewhere on the rubber ball. You hit it with a stick. Now that is going to cause some vibrations in the surface. Now these vibrations may have, I mean, when you have these disturbances, every disturbance we have may have higher order of disturbance inside itself. I mean, look at this. If you're able to see the screen right now, the red line is what the zeroth order was without any disturbance. Now, after you hit it with a stick, there is first order disturbance, which is this broad blue line, which is kind of the envelope of the blue line is nothing but the first order disturbance. But now when you enlarge it further, this blue line is not just not just that level of disturbance. There are higher level of disturbances in it, which is these tinier waves inside of this blue wave. So that is the second order disturbance. So that is what I mean by, and what we want to do with gravitational waves, the the information that we are actually concerned about, and what we actually care about comes from first order itself. I mean, we don't have to zoom in further to go and see what is there in the second order as of now. I mean, of course, later on, physics is going to develop to that extent, and we will look into the second order as well. But we don't need it right now. First order is good enough for us. So over here in our metric as well. So we have the total metric is nothing but flat spacetime metric, that is the local metric that we have, plus the disturbances. And what we want is not the higher order disturbances. So we just give up the higher order disturbances and we deal with the first order or the linear disturbance. Is that helpful? Okay. These disturbances go until what extent? Well, these disturbances, I'm not sure, but I would be bold enough to say that these disturbances go until infinity, because it's just like a Taylor expansion of anything that you have in your hand. You have some small quantity. If you Taylor expand it, you can. This is equally like asking a question that how long does the Taylor expansion go? It goes till infinity. Just the thing is that the later terms of this series are going to be so insignificant and so small that we don't care about them. We just don't care about them. Yeah. So these disturbances keep going on. I mean, till 100 years. I mean, till 100 years back from now, we did not care about this first order disturbance also. Einstein came and he told us that there is something beyond Newton as well. But Newton did not see it because it was 1 upon squared of speed of light. It was so small. It was so small in magnitude. So Newton did not care so much because he found something. Einstein said that no, there is something beyond it. So he he gave us a method to find higher order terms, and it goes on like that. Oh, and yeah, extra dimensions. No, I don't think so. Thanks, Surendra. Oh, how many terms matter? That's again a good question. Okay, that's up to the personal interest. I mean, yeah. So over here, I'm sorry I did not explain this part. So for a system, if we want to, for a let's consider a binary system again. If we want to see that, if we see that they are not going around a fixed orbit, but the orbit itself is precessing. Precision of orbit means there is an ellipse in which the objects are moving, and this ellipse itself goes round and round. It rotates. That is called precession of the orbit. I mean, Mercury does it, and that's the most famous example that we know of orbit precision. So yeah, if you want to explain that precision, if you want to explain that with your physics, then you have to go to the first order. Now, if you want to understand the spin of the bodies and the orbit going round and round, you have to go to 1.5 order. Next, if you want to see the effect of spin of one body and the spin of other body, and you want to see that, you want to understand the interaction between them, you go to second order. And the orbital decay as in the bodies coming closer to each other because they're giving out gravitational radiation or gravitational waves, that comes at 2.5 order. So it is totally up to us to what extent we want to go. But yeah, current state of art is 6 pn, I think. And we are getting everything as of now, whatever we want. We can obviously go to higher orders, but that is going to need a lot of computational power. So yeah, so okay, so that is how we decide to which Taylor expansion term we want to go. In my study, the study that I have done, I have hand calculated till the second order, which in itself was a little gruesome, and I don't suggest anyone to do that. I think that we should just understand these terms from the result that we have, and not actually go into trying these by hand. But of course, if you're interested, I would suggest that we just do it on Mathematica or some other computational platform. So that is up to us how far we want to go into this Taylor expansion. And I think there's this last question: why PN only work in weak field? Yeah. So okay. So we want post-Newtonian approximations. Post-Newtonian approximations start with Taylor expansion, right? Taylor expansions are for the quantities, or are for the stuff that is really small, really small. If you see over here, this h disturbance is 1 upon c square times smaller than the local space-time, smaller than the metric of the local space-time, or the curve. Yeah, basically it is very small. So if it is very small, that means that we are having a disturbance which is not comparable to the um, which is not comparable to really big disturbances which are happening at the source location. I mean, the source being whatever, like maybe binary going around each other, or maybe some star collapsing, or anything, gamma burst, anything. Yeah. So these h's are really small. And since it is small, that is why we are able to Taylor expand it. If it were to be not so small or significantly comparable, even comparable to the source, then that would mean that this Taylor expansion won't converge. Basically, we won't have a Taylor expansion. We'll have a series which is diverging. And playing with the diverging series is just that is not physical, that is not mathematical, because you don't have any end to it. And the effective value of the calculation, I mean, the effective measurements or the results of the calculations are never going to be achieved. Hence, we can't use post-Newtonian approximation to strong field, because at strong fields we have fields, or the h will be not as small, but it will be big, and we won't have anything on our hands. Okay. We work in weak field because for a perturbation series to make sense. Yeah, if you were to talk in terms of perturbation, the disturbances have to be small and it has to die out. Yeah. Are there any other questions? Did I miss anything?
Chinmay, I don't think that there will be any further questions.
Great.
Okay,
Great.
so we are also almost mm, beyond the time limit as well. But
Yeah.
yeah, it was a really great talk, Chinmay. Like, thank you so much for
Thank you.
giving such a great
And
talk.
if you have any questions, if anyone has any questions, please do write them to me on my email address, because I don't think I've been able to justify this topic in one single talk, which was just 1 hour long.
Yeah, I'm sure many of the participants
Yeah,
might have any questions, so they can just mail it to you directly.
sure.
So yeah, once
And
again,
sorry to
thank you so
interrupt. Yeah.
much for such an enlightening talk. Although it was
Thank you guys for
quite,
listening out. Yeah.
it was actually quite mathematical, but I'm sure that everyone must have learned a lot of things.
I,
So
I mean, yeah. I mean, trust me, it's not that rigorous, or it's not that hard, but yeah, you'll enjoy it once you get into it. And it's a little difficult for me to explain it now because I'm still just 1 year into it. Yeah.
yeah, that's great.
Thank you guys.
So okay, so we'll just wrap up by a closing statement that thank you everyone for joining us. We'll be having our next lecture tomorrow by Premada Kameshwar related to cosmology, accelerating universe, and sterile neutrinos. I hope you guys will be joining us tomorrow. So we'll see you then. Thank you so much for joining us. And
Thank you.
also one thing, this talk will remain on YouTube as well. So if anyone is interested to look back again and have anything else, this will remain on this YouTube channel as well. So thank you so much.